Let x0, x1, x2, dot, dot, dot be a sequence of numbers where each xk is either 0 or 1. For each positive integer n, define Sn as sum over k equals 0 to n minus 1 of xk times 2 to the k. Suppose 7Sn is congruent to 1 modulo 2 to the n for all positive integers n. What is the value of this following sum? Okay, so we have these coefficients xk are all the time 0 or 1, and we're multiplying them with 2 to the k and adding over k. So this suggests us using binary expansion. So we can write this as xn minus 1 dot 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 x1 x0 in binary notation. All right. So, and we have this weird condition, 7Sn is congruent to 1 modulo 2 to the n. Okay, so this tells us Sn is congruent to 1/7 modulo 2 to the n, but it seems complicated to find what 1/7 is modulo 2 to the n. So let's try to investigate further. So these Sn's, we observe that the right portion are always the same, and whenever we go from Sn to Sn plus 1, we add one more digit here, right, to the left of the number. So what if we add all the digits, all these numbers indefinitely, and define this expression as apple? It's not technically a number because there's infinitely many digits, but Sn is the last n digits of this number in binary. So let's work with this apple. Okay, so apple is, x3, x2, x1, x0, let's say. Now, the condition we had was 7 times Sn should be 1 modulo 2 to the n. Now, if you want to work with binary notation, we can write 7 as 1, 1, 1 in binary, but that seems complicated to multiply with 1, 1, 1. Doesn't seem very easy. An easier way would be to write it as 8 minus 1 and observe that 8 is 1, 0, 0, 0 in binary, and so minus 1. So multiplying by 8 is much easier because you just add 3 zeros to the right. It's the same as multiplying by powers of 10 in decimal notation. So since Sn is the last portion of this apple, we can work through with apple and then say that the last portion is going to be what we have Sn. So let's write 8 apples. It's going to be x3, x2, x1, x0. And then we have 0, 0, 0. Binary. And then if we subtract 1 apple from this, so x2, x1, x0, x3 here, x4 here, etc. Then the difference is 7 apples. And the last portion, last n digits of this should give us Sn. Right? And that should be 1 modulo 2 to the n. So that means the last part of this is 0, 1, 0, 0, 0, right here. Okay, and this is true for all n, all positive integers n. So we should have this difference in binary subtraction. So from here, let's go back to red. So 0 minus x0 should be 1 in. So from here, we get that x0 should be 1, right? x1 should be 1, x2 should be 1, right? And then if we get those here, then we get 1 minus x3, but there was a carryover here, from 1 to here. So there's only 0 left there. So x3 must be 0. And this time there's no carryover anymore. So 1 minus x4 should be 0. That means x4 is 1. And then this is also 1. So we can continue like this. When we have x3 is 1, 0, x4 is 1, x5 is 1, etc. We continue and find earlier digits. See, this was x5, x6. So we need to do this until we find a pattern. Okay. x2 minus x5 should be, yeah, there's no carryover anymore. So this should be 0. And this should be 1. This should be 1. So we see that there's after the last digit, basically, there's a pattern of 1, 1, 0, 1, 1, 0, 1, 1, 0. And there's no more carryover in the earlier subtractions. So this pattern continues throughout. So we find that x0 is 1. And aside from those, if the index is a multiple of 3, we get 0, and otherwise we get 1. And for the problem, we need to find out, so the multiples of 3 indices give us 0, all the other terms give us 1. So let's go back to what the problem was asking. 2019 is a multiple of 3, so that should be 0, and all the others are 1. And 2022 index is also a multiple of 3, so this is also 0, and the other two are 1 each. Because they are not multiples of 3, the indices. So the sum we get is 6. The answer is A.